Hello everybody, and welcome back to another geometry lesson. Today we're taking a look at, well, Unit 4. The thing about Unit 4, transformations, is that we have talked about these transformations before in middle school many times. Because of that, we've shortened Unit 4 down a little bit, and we're going to sort of go over an overview of all of the concepts today. That's going to be sections 4.1 through 4.3, as well as section 4.5. So, let's take a look at some of the definitions. To start off, we'd start talking about a vector. A vector is a quantity with direction and magnitude. If you've ever seen the movie Despicable Me, you can think about the villain, Vector. Always has direction and magnitude. But what does that really mean? Well, something that does have direction and magnitude is another word for size, is an arrow. So we will usually represent vectors with an arrow. Let's say this is our vector. This vector is going up towards sort of the top right portion of my paper. We can break up this vector's direction into two pieces. We're going to the right some amount, and then we're going up some amount. These are called the components of a vector. So let's pretend for a second that we went 5 units to the right and 3 units up. Our vector would be going in the top right direction, or upright direction, and would have a magnitude of 5 units to the right and 3 units up. We can write this in a form called component form, where we just write out how much in any direction the vector moves. So this vector is moving 5 units in the x direction and 3 units in the y direction. So we write it as 5, 3 in these angled brackets. So that's what a vector is. Why do we care about vectors? Well, because when we're starting to talk about vectors, we're talking about moving something from one point to another. For instance, imagine there was a dot right here at the end of the vector. We could move that dot 5 units to the right and 3 units up, and we would be performing something called a translation. A translation is a transformation that shifts or slides each point of what we call a pre-image to an image. In plain English, a translation is sliding a shape or a different figure from one point to another. If I had some sort of square here, and I want to do a translation, I would be shifting that square and sliding it across my paper to the right and up some amount. I'd be shifting each of the 4 points of that square until I got my image. We call the original shape, or the original figure, a pre-image, and we call the new shape an image. So whenever you see me say the word pre-image, think about me saying the original. Whenever you see me say the word image, think about the transformed version of a thing. Let's see an example so we can work through these definitions. In exercise 1, we are asked to use the graph to perform the following. First off, we are told the vertices of triangle ABC are A at 0, 3. This is where A is. And as we go along, you're going to label all of your points, but label them relatively small. We're going to have a lot on this graph. We've got A at 0, 3. We've got B at 2, 4. And we have C at 1, 0. Perfect. Now, since we're trying to make triangle ABC, let's connect these up using a straight edge. It's at this point that I want you to know, for this section, you're going to need a straight edge, a compass, and a protractor. So I'm going to connect all these points together to form triangle ABC. And then we're going to do some transformations to it. We're going to change its position. We're going to change its orientation. The next part tells us to translate ABC using the vector 5, -1. Again, translate means to slide this shape around. So we're going to be moving this shape somewhere else on this graph. The vector, in component form, tells us how to slide it around. Remember that in any pair of points, we'll usually refer to the first number as x and the second number as y. So this is telling us to move 5 units to the right and 1 unit down. So let's start at point A and move 5 units to the right and 1 unit down. If I start moving 3, 4, 5 units to the right and 1 unit down, I get this point right here. This is where point A would be if it was moved along the vector 5, -1. Now, I want to label this point A because, again, all we're doing is taking the shape and moving it. It's not like we're changing the letter of the point. But the problem is we can't have two of the same letter on a graph. So mathematicians solve this by labeling this as A prime, where this little parenthesis up top stands for prime, or another version of A. Whenever you make a new version of a shape, you're going to add a prime symbol. If you make a new A after this, like a third point A, it'll be A double prime with 2 prime symbols. If we make a fourth point A somewhere on here, it would be A triple prime. You get the idea. So let's shift all of these points along the vector 5, -1. So B prime is going to end up right here, and C prime, 1, 2, 3, 4, 5, and down 1, it's going to end up right here. Perfect. So we would label this triangle as A prime, B prime, C prime. Remember that when you are naming a triangle, you name it based off of the vertices that make it up. This is triangle A prime, B prime, C prime. Nice. Now it's asking us to write a rule for the translation of triangle ABC to triangle A prime, B prime, C prime. Whenever we are writing a rule, here is how we do it. We're basically making a before and after. To do this, we are going to be using an arrow. Here's how most rules are going to look. If you're starting from the original shape, you're starting from all of the shape's original x and y points. Like A, point A, had the x and y of 0 and 3. But what's changed? As I go from 0, 3 to wherever this point is, what did we end up doing? Well, let's take a look at each component of our x and y and see what changed. So what happened to our x value? We started at 0, we ended at 5 for point A prime. For point B, we started at 2, B prime ends at 7. C starts at 1 and ends at 6. all we did was we added 5. So our rule for the x values is we changed x into x plus 5. As for the y values, for point A, we started at 3. A prime is at 2. For point B, we started at a y value of 4. B prime has a y value of 3. We see that we are just subtracting 1 from our y values. So this is how you write a translation rule. You write down what you had before, x and y's, then write down what you have after. What I want you to do is this. Pause the video and see if you can graph the image of triangle A prime, B prime, C prime after this translation. And before you do, be careful. If I'm asking you to graph the image of triangle A prime, B prime, C prime, I'm telling you that A prime, B prime, C prime is your pre-image. We're treating our blue triangle as the original, not our black triangle. So treat the blue triangle as the original and do the following transformation. Pause the video now. How do we do? Hopefully we saw that from this transformation, we had to take all of our x values and move them 2 to the left, since we're subtracting 2 from our x values. Then we asked to move all of our points down 3, because it says y minus 3. Very nice. Let's, before we flip the page, take a look at a couple more definitions. What we have just done is something called a rigid motion. When you look at these triangles, did we end up changing the shape or the size of these triangles? No, they're all still the same triangle, right? Well, that's what makes a motion a rigid motion. A rigid motion is a transformation that preserves angle measures and side lengths. It's a transformation that preserves angle measures and side lengths. So overall, any motion that doesn't change the shape is going to be called a rigid motion. One such case of a rigid motion is something called a reflection. And when you think of a reflection, we usually think of a mirror image. So if I drew some amorphous blob here, something that looks like this, and I wanted to reflect it over the dashed line, we're imagining this dashed line like a mirror, and we're trying to find the mirror image. This is where we have some tools that can help us. So in class, we have a couple of these purple plasticky mirrors. They barely look like mirrors. They don't reflect 100%, but these are called geomirrors. The point of a geomirror is you're supposed to stand it up with the sharper edge facing down on your line of reflection. And if I tilt the camera, actually I don't even need to tilt the camera, you can already see the reflection. The idea is that a geomirror is a tool you can use to help you draw out the reflection of a shape. Boom, I've just drawn our reflection. So when we talk about a reflection, we have a very specific definition to give here. A reflection is a transformation which flips an image, which flips a pre-image over what we call a line of reflection. A transformation which flips a pre-image over a line of reflection. So as we go to the next page, keep in mind that you're always going to need a line of reflection, and then we are flipping over that line. So let's take a look. Whenever you are presented with a graph, a reflection is pretty clear to picture. Like we said, a geomirror is one tool we could use to see both a pre-image and to reflect its image on the other side. But if you don't have a graph, like we do in these examples, you need to reflect point by point. So we have some coordinate rules for reflections. These rules are very situational, and that's why we're going to make sure that you have these with you as we do our end of unit project. But these are 4 rules that are shortcuts for reflecting something. It doesn't work for all reflections, but anytime you're trying to reflect over the x-axis, the y-axis, the line y equals x, or the line y equals negative x, we have some shortcuts you can do to reflect. For instance, if you're reflecting something over the x-axis, in other words, turning it upside down, then the image just has all the y values flipped upside down. It turns all the y values negative. Just as one example. But let's do some reflections here on graphs, and then we can use our rules to help us do the rest of the reflections. So on exercise 2, we've got a smiley face, and we are asked to reflect this shape in the line x equals 1. The line x equals 1 is going to be the line that cuts through an x value of 1. So it's a vertical line. This is the line x equals 1. And we're asked to reflect this shape in the line. In other words, that means to flip it over the line. So if you want to use your geomirror to help you out with this, this is like the perfect way to do so. Start by placing your geomirror right on your line of symmetry. There we go. Look through it, and on the other side, you'll see exactly where your points need to be. So if you wanted to use the geomirror here, for instance, it's going to be a little bit tricky with my current positioning. If you could see the weird ways I'm contorting myself to fit my pen in here, you'll laugh. But I can actually see where these points are. I know, for instance, that the smile of my smiley face is going to start right here, and it's going to go sort of down to this point, then back up to this point. It matches when we take the mirror away. So that's one tool you can use to help you out. But I want to show you what to do even if you don't have that tool. Oops, I realized I made a slight error as well. I apologize. And I'll show you why there was a slight error. There's a slight error because I believe, yep, as we can see here, I goofed up. I'm so sorry, y'all. When we made the smile, we made it a little bit too close to the edge, and I'll show you why in a moment. As we look at the smiley face, we see that this edge is 1 space away from the dashed line. So it has to be the same on this side too. This is going to be part of our circle. I accidentally made it part of our smile. We can see that the top edge of the circle is 3 spaces away. So we go 3 spaces in the other direction. The top part of our circle is going to be there. We can repeat this process over and over again until we have basically where our circle should be. Our circle is supposed to be right here. So now you'll see that my smiley face is sort of swayed to one side. We could repeat the same process with the dots for the eyes. 1 dot is 2 squares away from the line, so we go 2 squares in the other direction. The other dot is another 2 squares after that, so 4 squares away. And the smile is supposed to go right here. So ignore the black line here. Again, I apologize, folks. But the green is where we're going to have our reflection. That's how you can reflect over just any line. Now, on this problem, we're asked to reflect the shape in the line y equals x. This is a bit trickier. The line y equals x is an equation that says every y value should equal every x value. So what are some points where the y and x values are the same? Well, here y is 1 and x is 1. Here y is 2, x is 2. Here y is 3, x is 3. And so on and so forth. The line y equals x is a diagonal line that has a positive slope. So this is the line y equals x. Since we're asked to reflect over this, I can show you what it'll look like on the mirror. On the mirror, if I put it down right here, we'll see that something strange happens. You're not able to see the whole triangle. You're able to see part of it for sure. Like we can tell that, for instance, this point here is going to be at 1, 5. But you're not able to see the whole triangle. So instead, we need to be creative with how we are going to approach this problem. This is where the coordinate rules for reflections come in. One of our rules is if a point A comma B is reflected in y equals x, then look what happens to the point. We switch the second number and the first number and get a new coordinate. What do I mean by this? Well, let's take a look at our image, or our pre-image. On our pre-image, this point down here is at the coordinates 5, 1. If this point's at 5, 1, and the rule is that you're supposed to switch your x and y values, then our new point should be at 1, 5. According to this, according to our rule, I should say, this is where the edge, or the tip of our triangle, I should say, should be. If I place down my geomirror, again, we can see that this is, whoops, I didn't line up my geomirror properly. We can see that this is true. 1, 5 is right here. So we can repeat this with the other points as well. The original point on this side ended up being 3, 4. So where will our new point be? It'll be at 4, 3, the flipped version. Notice that this point over here in the corner is 2, 2. But as we look at this, these numbers are already the same. Even if we flipped them, they would still be the same. So that means that our reflected point is actually on the line of reflection, right where it originally was. If we take our ruler and start to trace out where these points are, we can see that this is the case. There's our first connection, there's our second connection, there's our third connection, and if we take a look at this, look at that. It looks the same on both sides. If I tilted my paper 45 degrees, it looks like it's been cut in half. What I'd like us to do now is this. I want us to use the rules for reflections, the ones that we highlighted, to help us with B and D. I'm asking you to do 2 transformations to a point. I'm asking you to first, for part B, reflect it, then shift it or translate it. For part D, I'm asking you to do the opposite. I want you to pause the video. Try to figure out what the new point is going to look like, and come back when you are all done. How do we do, folks? For point A, once we reflect it over the x-axis, the rule says that if AB is reflected, A stays the same, but B becomes negative. So our x value stays 2, but our y value turns to -3. After that, we have a translation where we remove 5 from our x and remove 1 from our y, we get -3, -4. But as we can see in the second part, the order of how you do transformations matters. Take a look here. If we start at the point 2, 3, and we do our translation first, subtracting 5 from the x, subtracting 1 from the y, we get -3, 2. And as we know, reflecting over the x-axis means we keep our x the same, but flip our y to be negative. We get -3, -2, a different point than A. So be careful when you're asked to transform something multiple times. Anytime you're asked to transform multiple times, we call it a composite of those transformations. Bear that word in mind. All right. Let's flip back to our definitions page. I want to talk about line of symmetry. It's something I want to talk about very briefly because many of us have already seen lines of symmetry before. But if I have some shape here, say I have a rectangle, a line of symmetry is any line you can draw through a figure such that it looks the same on both sides. So one line of symmetry for a rectangle is splitting it down the middle this way. That's a line of symmetry because if I cover up the right side, the left looks the same as the right. Another line of symmetry for a rectangle is cutting it in half this way. How does one find lines of symmetry? We sort of have to visualize what a shape might look like. One thing you can do is you can cover up half of a shape and shift your hand around until both halves look the exact same. You can do this very nicely with a ruler. Just be careful. If I was to try and make a line of symmetry diagonal to here, we see that we have a short edge close to the ruler and a far edge sort of further down on it. This rectangle is a far edge close to the top of the ruler and a short edge further down on it. This would not be a line of symmetry because it is not the exact same. It's reversed on the other side. So definitionally, when we talk about a line of symmetry, we are specifically going to be talking about when a figure flipped over a line of reflection has an identical image. Fantastic. We're making great progress, y'all. I think it's time we start talking about rotations. Rotations are fun. Rotations have a lot of very interesting mathematical properties that we're going to be discussing. But first, I want to talk about what a rotation is. Put simply, a rotation is going to be any time you tilt a figure in a certain direction, or you twist it or turn it. If I had point A at the top of my triangle, for instance, and I turned it 90 degrees clockwise, point A would be on the right side of the figure. When we talk about rotations, we're usually going to give it some degree of rotation, how far we want to turn it, and some sort of direction. So, a rotation is a transformation in which a figure is turned about a fixed point called the, and we're going to call this term the center of rotation. When we talk about a center of rotation, all shapes have to rotate around something. When you rotate a shape for instance, rotating our triangle A here, there was some point that we rotated it around. There's no better way to describe this than to actually do a rotation. So let's flip to page number 3, but we will be flipping back to pages 1 and 2 in just a little bit. On page 3, we have to use a protractor, told you need one, and a ruler to rotate triangle ABC 120 degrees about point P. When we are asked to rotate a shape in math, we are usually going to be rotating it counterclockwise unless otherwise told. So what we're going to be doing is taking, for instance, this side right here, CB, and we're going to be rotating it until it's 120 degrees, or it forms a 120 degree angle between the original and the new. But we're not rotating it around point C like I showed you on my protractor. We are rotating around point P. Imagine point P being at the center of a big circle, and our triangle is rotating around that circle. That's what we are doing. So how do we do a rotation like this? Well, there's a couple of steps, but this is going to be almost like a construction. So let's take a look. Step 1. To rotate a shape, you need to rotate each point individually. To do that, we are going to start by drawing a line from one point to the center of our center of rotation. So I'm going to draw a dashed line going from our center of rotation, point P, to our triangles, point A. Now, remember what I said before. A 120 degree angle of rotation is going to take us from having a straight line this way to making a 120 degree angle between there and our new point. So here's how you do it. Take your protractor and place it centered on point P. Now we need to line up our protractor so that this line going through the middle of it matches up with the line we just drew to point A. So right about there, looks like it's matched up pretty perfectly. On the protractor, we've got measurements. And if we're trying to open up an angle that goes this way, let's count out using the numbers going around this direction. 10, 20, 30, 40, 50, 60, blah, 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 blah. A 120 degree angle would be drawn if we made a line from our center of rotation to the number 120. So what I'm going to do is I'm going to mark off 120 and its opposite side as well. So I get 2 very small points. I wouldn't even make these dark points. And I'm going to repeat the line, but this time going from point P through those 2 points. So here we go. I'm going to make this line pretty long. It's okay to have a little bit of extra line at the end. There we go. What we've just done is we've drawn a line here and then made a 120 degree angle going from point A to this direction. Now, if we want to rotate this shape, we can't just place it anywhere we want along this line. We need to make sure that the position matches up. This is why you need a ruler. You can measure the distance from point A to point P. Now, you can do this in inches. This is where we're going to have to remember our ruler skills we learned in Unit 1. If you're measuring it in inches, for me, this distance is 1 13/16 inches because it goes from 0 all the way up to the third line before 2. Or you can measure it in centimeters, and this line looks to be just about 4.6 centimeters. Is that right? No, you know what? 4.6 is a good estimate. So 13/16 inches or 4.6 centimeters. However you want to measure it, you're then going to copy that length to the other side. So I'm going to use the inches. I'm going to place my ruler down so that we have 0 over here and 1 13/16 over at point P. And I'm going to make a dot. This dot is the location of A prime, because this distance was the same. So in short, here are the 4 steps. Step 1, draw a line from the center to your point. Step 2, use your protractor, line it up on the line you just drew, and mark off where a 120-degree angle would be. Draw that line out, and you'll get a 120-degree angle. To figure out where on that line you have to draw your point, measure it out. Measure out how far the center of rotation is from your point, and copy that distance down on the other side of the angle. I want you to try to do this with points C and B. Take a couple of minutes and see if you can rotate these other 2 points. Pause the video and try it out. How'd you do? If you did your steps correctly, your triangle should look something like this. But how can you tell if it's perfect? Well, there's a little way to check that I've implemented into this very problem. You see, when I made this worksheet, I made sure that triangle ACB was a right triangle. So if you want to check, use the corner of a piece of paper to make sure this is a right triangle. ACB matches up perfectly, so it is a right triangle. Let's check out A prime, B prime, C prime. If I line up my piece of paper, it makes a right angle. So I know I have done it correctly. Very nice, y'all. At this point in time, I want us to move on to exercise 4. But I want to show you a different way of rotating that doesn't involve using a protractor. Believe it or not, there are mathematical ways of rotating. So this says to graph triangle ABC with vertices at 2, 5, this is point A, 1, 2, this is point B, and 4, 3, this is point C. So we've got triangle ABC on here. And we are asked to rotate this shape 90 degrees, 180 degrees, and 270 degrees. Well, if we want to do this with a protractor, this would take ages. I mean, you saw how long that first one took. So instead of rotating with a protractor, I want us to flip to the previous page to look once again at our rules. So in addition to the rules for reflections, we also have rules for rotations. It tells you exactly what happens when you rotate 90 degrees, 180 degrees, and 270 degrees. But I've also got a little bit of a shortcut to help you memorize these. You won't need to memorize these. Again, you'll have these notes with you when you do your project, but it's very nice to. Here's the rules for rotation, 90 degrees. Anytime you rotate a pre-image 90 degrees, there's 2 things you have to do. Number 1, swap your x and y values, so flip them backwards. Number 2, change the signs of x and y to match the quadrant they're in. Recall that whenever you have a graph like, well, let me flip back to the example. Whenever you have a graph like this, there are 4 quadrants. You've got quadrant 1 in the top right corner. Then you move counterclockwise to quadrant 2, quadrant 3, and quadrant 4. The points in these quadrants all have certain signs. So for instance, in quadrant 1, we've got all of our positive x values, all of our positive y values. So no matter how you rotate it, if your point ends up in this quadrant, both of your values should be positive. If you're in quadrant 2, something changes. In this quadrant, our x values are all negative. Negative 1, negative 2, negative 3, negative 4. But our y values stay positive. So no matter what happens, anytime a point ends up in this quadrant, its first number is negative, its second is positive. We can keep going around the circle, seeing exactly what happens when you move to certain quadrants, and we have painted a very good picture of what each point should look like. So let me give you an example. If I try and rotate the point 2, 5 around, the rule is every time I rotate it 90 degrees, I swap the order of the points, but I have to make the signs match the quadrant. So if I take 2, 5 and I rotate it 90 degrees, I'm going to get 5, 2. It's flipped. But in quadrant 2, the first number is negative. So we're not graphing 5, 2, we're graphing negative 5, 2. I'm going to use red dots to mark off where point A is. So negative 5, 2 is where A prime is. Let's rotate it again. So here we have negative 5, 2. What happens if I rotate it 90 degrees again? Well, the rule is the order of the points flips. So instead of negative 5, 2, it'll be 2, 5. But in quadrant 3, both numbers have to be negative. So it'll be negative 2, negative 5. This is where point A double prime is at negative 2, negative 5. Finally, if I want to rotate it one more time, I need to flip the order of the numbers again. So instead of the 5 being second, the 5 will be first. It'll be 5, 2. But in quadrant 4, the second number is always negative. So it's not 5, 2, it's 5, negative 2. We have rotated one point of our triangle all the way around the coordinate grid. Could you take a moment to pause the video and rotate points B and C around the coordinate grid as well? Pause the video and give it a shot. Hopefully you've had a chance to try this one out. If point B is originally at 1, 2, then point B prime is going to flip 1 and 2, because we're rotating 90 degrees, to be at negative 2, 1. If we flip it again, instead of negative 2, 1, it'd be negative 1, negative 2. Again, we switch the order. So that's where B double prime is. Oh, whoops. I didn't realize I'd marked off A triple prime incorrectly, so sorry about that. If we swap it one more time, instead of negative 1, negative 2, it'll be 2, negative 1. We just make sure that the 2 is the first number. So that's where B double prime is, or triple prime. Point C, the coordinates are 4, 3. So when we flip it around, it gets to 3, 4. But again, we're in quadrant 2, so it's negative 3, 4. We flip it again, it goes back to being 4, 3, but it's negative 4, negative 3. We flip it one more time, it flips back to being 3, 4, but it's 3, negative 4, because we're in quadrant 4. So we've got our new triangles. Now I'm just going to freehand these triangles, even though it'll look a little bit not great. You would be using a ruler to draw these lines. I'm not trying to sit here and waste your guys' time. We've rotated it. Very nicely done. We've got one more thing we're going to do, one more type of transformation. So let's flip back to the front page where we are going to talk about my favorite one. It's a transformation called dilation. Now, why is my favorite? Because this one has so many real-world uses. Anytime you are trying to go from a sketch to a real-life project, you're using dilations. Anytime you are going from something big to drawing something small, it's a dilation. A dilation is a transformation in which a figure is enlarged or reduced. It's either being made bigger or smaller. So this transformation will either increase or decrease the size of all of our lines. How much it increases or decreases is going to be based off of some scale factor, something we call a scale factor. Let's say the original shape had a length of 2 units, and I wanted to make it 3 times bigger. My k value is what we would call our scale factor, being 3, means we want to take this number and multiply it by 3 to make it 3 times bigger. As long as you are multiplying every side by the same scale factor, you will make the figure 3 times larger in this case. You could have a scale factor that's a fraction. Maybe you're multiplying all the sides by 1/2. Well, that would make them all smaller. So when we talk about a dilation, it's making something bigger or smaller, and it's all based on what this number is. So a dilation is a transformation that enlarges or reduces a figure by a scale factor that we're going to call k, with respect to some center of dilation. Now, much like we had a center of rotation, what you're also going to have is a center of dilation. This is some point that tells us, hey, here's where you're starting, here's where you're ending up. To find the center of dilation, what you have to do is trace a line that goes from every side and see where all of them meet up. So if I had enlarged this factor or this image correctly, it'd be a little bit easier. But it looks to me like if I was to draw all 3 of these lines, they sort of meet up right here. The center of dilation is just the point where all of your dilation happens from. This won't really come into effect until we do our last problem. But let's take a look, once again, at our last page. For exercise 5, we are asked to graph triangle ABC with the following vertices. We're going to graph ABC with the vertex at 2, 3. That'll be point A. 1, 2. That'll be point B. And 4, 1. That'll be point C. So our triangle is going to look like this. There we go. There we go. And there we go. Perfect. We're asked to dilate triangle ABC with a scale factor k equals 2, then with k equals 1/2. So this is asking us to make it 2 times bigger than 1/2 the size. Now, unless you're told otherwise, we can treat the center of dilation as the point 0, 0. But here's how you make a dilation happen. Take your points. So if we have A at 2, 3, and multiply them by your scale factor. So if we're trying to make it 2 times bigger, multiply your x by 2 and your y by 2. So if you multiply our x by 2, we get the point 4. If you multiply 3 by 2, we get the point 6. So 4, 6 is where we could place A prime. Again, because it's just 2 times bigger. Multiply your x and y's times 2. We can repeat this process for the other points as well. So B had the coordinates of 1, 2. If I multiply both of those by 2, I'm going to end up getting 2, 4. So 1 times 2 is 2, 2 times 2 is 4. B prime is right there. So if I, once again, multiply that by 2, I get B prime. Maybe I should draw this arrow a little bit more towards point A so we can see that clearly. There we go. For point C, we start at 4, 1. So we multiply those by 2. 4 times 2 is 8. 1 times 2 is 2. C prime is all the way over here at 8, 2. And again, we get that because we multiply both our x and y by the number 2. So let's map out our triangle, our image, and see what happens when we compare. By multiplying all of our coordinates by 2, we have now made this shape 2 times larger. Just compare the two of them. If I was to measure out the sides, let's say this is about 1.2 centimeters. This is about 2.4 centimeters. So it's twice as big. Now, if I wanted to do this with k equals 1/2, I need to multiply our x and y values by 1/2. So let's start with point C. What's 1/2 of 4? Well, that's 2. What's 1/2 of 1? Well, that's 0.5. So point C double prime is going to be at 2, 0.5. That's where our new dilated point is going to be. If you repeat the process with the other points, so B is at 1, 2. If we cut both those coordinates in half, we get 0.5, 1. That's where B double prime is. And A was at 2, 3. Half of 2 is 1. Half of 3 is 1.5. A prime is going to be right here, or A double prime is going to be right here. We have just made a triangle that is half the size of our original. And our original is pretty small to begin with. So this one is absolutely tiny. But once again, all we did was we cut all of our lengths in half. That is how you dilate a figure. And if I was to check where the center of dilation is, by lining up, for instance, all 3 of my point C's, you'll notice they all line up with 0, 0, our origin. So that's how you dilate a figure. You just multiply the x and y coordinates. Last, but most certainly not least, for exercise 6, we are going to be using a compass and a straight edge to construct a dilation of PQR with a scale factor of 2. So if our scale factor, k, equals 2, what are we doing to it? Well, we're going to be enlarging it. We're going to be making it 2 times bigger. This is a 3-step process. So I wanted to show you how it is done. Step 1. Just like before, we know that a center of dilation is in line with every possible dilation of a figure. So what we're going to do is we're going to draw lines that extend out from every single point to the center. So here's a line going through point P. Here's a line going through point Q. There we go. And here's a line going through point R. You're going to want to make these lines relatively long, for reasons we will see in just a moment. So step one is to draw lines connecting every point to your center. Step two is this, and this is much easier if you have a compass with a point on it rather than our rotational compasses, but a rotational compass will do just fine still. You need to measure the distance from C to P. You could do this with a ruler, but since we mentioned we're doing it with a compass and a straight edge, here's how you measure with a compass. Place the center of your compass down at your center of dilation and find which hole matches up with your point. For me, it's going to be this one. It's going to be the point after the letter C. What you're going to do now is you're going to move your compass so that your brass center is on point P and make a dot at that same spot. So 1 point after C. You could also make a small arc if you would like. Take a look at what we just did, and I'll make the arc at point P just so you can see it, but you don't need to mark off this arc. Take a look at what we just did. If this distance is one space away from the center, the space between C and our new point is 2 spaces away. We've just multiplied the distance by 2. So P prime is going to be at a distance that's twice as far from point C. This is actually going to end up dilating it by a scale factor of 2. So let's repeat the process. Lay my compass down at point C. I'm going to see what matches up with point Q. It looks like A1, this marking right here, the first part of A1, is going to match up perfectly for me. So once again, I'm going to take my compass. Whoops, I'm going to extend this line out a little bit longer. I think I made my line a little bit too small for this one. That's okay, you can always go back over and remake your line if you need to. That should be good enough, even though it goes a little wavy at the end. If I then take my compass, place it on that point, and find where A1 is, that is where I'm going to place point Q prime. I can repeat the process one more time. I'm going to have my compass on point C. I'm going to find which hole matches with point R. It looks like with point R, it really could go either way. Either you could use this one right after L, or this one right before O. I'm kind of thinking it's closer to this one after point L, so I'm going to make an arc. And I'm going to repeat that arc right after here on point L, and call that R prime. If I connect up all 3 of these points that we've just made, I will end up with a triangle that is twice as big as the original. Anytime you are dilating to make a shape bigger, you can always just repeat this process over and over again until you get the length you're looking for. But this is our new triangle, P prime, Q prime, R prime. And it looks twice as big as our original. So that's it, everybody. Believe it or not, that's the end of Unit 4. Told you it was going to be a little bit of a shorter unit, considering it took about an hour to teach it. Have a fantastic rest of your day, everybody, and I will catch you next time.